Right, so as you remember, the limit of a function, right, at a specific point is basically where is the y value of the graph or the function approaching as I approach a specific x value. So suppose, this is my function here. It's just a linear function. Here's some point on the x-axis c, okay? As I approach c from the left-hand side, you see how the y values are decreasing and they're approaching this y value of L, right? As I approach C from the right-hand side, you see the y values are increasing and they're approaching this value of L. Because from both sides, the y values are approaching the same L value, we say the limit as x approaches C is L. Did we ever talk about what is the actual value at x equals c? No, that we don't care about. We just care about what value is it approaching, from the left or the right. So let's take a look at this function for a minute. This is the limit as x approaches -1 of 4x plus 1. We're going to estimate this using a graph. So let's go ahead and graph 4x plus 1. Right? So we know how to do that. 1, 2, 3, 4 over 1. Okay, it helps to do these things with a ruler. I already messed up here. I might just use a ruler myself. Here. I don't know why I can't draw a straight line today. That's not any better. All right, I don't know why it's not working today. Okay, so as x approaches -1, right, we want to see where the y value is approaching, all right? So it looks like here it's approaching this value of -3, right? As I get close to -1 from the left, and as I get close to -1 from the right, do you see how from the right the y values are going down to -3, and from the right they're going up to -3, okay? So we say the limit is equal to -3. We say the limit of 4x plus 1 as x approaches -1 is -3. Now, we did that graphically. In calculus or in mathematics, there are always 3 ways to solve something: graphically, numerically, and analytically. This is how we do it graphically. You just look at a graph, okay? Numerically, you basically put in, right, different y value, different x values, and ad nauseum basically, and you try things out. So here is -1. This is the number we're approaching. I'm going to approach -1 from the left-hand side, right? So first it's -1.01, then it's -1.001, and let's see what the y values are going to be. So if I put -1.01 into the function, I get -3.04. The next one, I get -3.004. So you see, this way, it looks like the y values are approaching -3. Now let's look at it from the other side. From the other side, to approach -1, right, it's -0.9 here. Then if I get closer, it's -0.999, right? So let's do that. I get -2.6 at the very bottom, -2.996 here. So as you approach -1, the y value is again approaching -3. So that confirms that the limit is -3, right? That's how we do it numerically. That's how we do it graphically. Okay? All right. Now, again, I can't stress this enough. Take a look at these for a minute. Look at this. This is the value of C. As I approach C from the left, the y value is approaching L. From the right, the y value is approaching L. The limit of this is clearly L, okay? But what is the actual value at C? What's f of C? There's a hole there, so it doesn't exist. It's undefined. Did that change the fact that there is a limit of L? No. Take a look at the next one. From the left, it's approaching L. From the right, it's approaching L. The limit is clearly L. This is g of x now. G of C, however, there's a hole here, but there's a point there. G of C is not undefined. It's actually another value of n, right? Not L, but another y value of n. Does that change the fact that there is a limit of L? Not at all. Finally, in the last one, the limit is clearly L, and what's f of C? Also L, right? So do you see how the actual value is completely independent from the value of the limit, right? One has nothing to do with the other. Okay, so let's take a look at this one. We're experts at, graphing rational functions now. If I rewrite this function, right, and I factor the top, the x minus 4's cancel, so what I'm left with is the limit as x approaches 4 of x plus 4. Okay. So now, let's go ahead and graph this x plus 4. Oops, 4. I'm going to go up 1 over 1. Okay, it looks like this. Is that entirely correct? At -4, I'm sorry, at x equals 4, there's a hole, right? Right here, there's actually a hole. There isn't a graph there, okay? So what is the limit here when you look at the graph? What is the limit? What y value is it approaching as you're approaching that point? 8. Right? So the limit is 8. What's f of x? What's f of 4? Undefined, okay? And as you do it numerically, right, as we're approaching 4 this way, am I too loud?
Oh, no.
Oh.
Jordan?
Jordan Schultz, she's taking her IP test.
Oh. Sorry for that.
It's okay.
What are you learning?
I thought it was limits.
Oh my
We're learning limits.
Dude, limits are the best.
They are. There is no limit to how much.
I see what you did.
Yep. Okay. So this gives you 7.99. This gives you 7.999. Do you see how it's approaching 8? And similarly from here, right? We get 8.01, 8.001. Again, it's approaching a value of 8. Okay? Yep.
How do you find the f of x value?
The actual value? You would plug it in, but it's unnecessary. Like, you don't have to do it to find a limit. It's irrelevant for a limit. Okay? Okay, so a little note for your homework. Do show the graph of the functions on your paper. And of course, you can use a calculator to do a quick sketch of the complicated functions. Like for the easy functions, it wastes time with the calculator, but okay. And then, estimate the limit by observation. You don't need to make the table like we did here. We just did that for you guys to see. It's not necessary, okay? Okay. So let's talk about one-sided limits then. Okay, let's talk about one-sided limits. Sometimes we don't need to see the limit from the left and the right side. Sometimes only one side is all we need, right? There is a special notation for that. And if we're looking at the limit from the left-hand side, the notation is this: limit as x approaches c from the minus side. If we're looking at a limit from the right-hand side, it's the limit as x approaches c from the positive side, okay? Now, How do we know if there is a limit? Well, the notation is if the limit as x approaches c from the positive side is equal to the limit as x approaches c from the negative side, then we say the limit is L. Okay? All right. So let's take a look at this. Let's find the limit of this function as x approaches 0 from the minus side. So here's x equals 0 right there. Okay. X equals 0, x approaches 0 from the negative side is to the left of 0. To the left of 0, what y value is the graph approaching? 5. So this is just 5. That's all you need to look at. You don't look at the other side. Now for the other one, x approaches 0 from the positive side. From the right-hand side, where is the y value approaching? 5. Because these two are the same, this is also 5 automatically. Okay? Now, how about as x approaches negative 3 from the minus side? So here is negative 3. From the minus side, what y value is the graph approaching? 0. From the positive side, where is it approaching? 5. Because these are not the same, they're not equal, this is DNE. Okay, incidentally, what's f of 0? Hang on, what's f of 0? 5. Do you see how the limit is 5 and the value is 5? Fine. Here, what's f of negative 3? 2, right? It's a completely different value. Okay, undefined versus DNE. The limit is never undefined, it's always DNE. The limit is always DNE. For the y values, we usually say undefined. Okay? Let's try to keep those separate. Okay? Was that your question?
Yeah.
Yeah. Okay, so let's take a look here very quickly. Let's do this. Okay, so ones like this, you have to be able to do it with just the function or by drawing the function. So let's just do it with just the function. Look at this here. The partition is at x is 1, right? So at x is less than 1, we've got this function. At x is greater than or equal to 1, we've got that function. So now here, when it says x approaches 1 from the minus side, this is the side less than 1, so we are going to use this function. And if you plug 1 into that, what do you get? 3. Okay? For the next one, when it's 1 plus from the positive side, we're going to take the function to the right of 1, so we're going to use this function. And if you plug 1 in there, you still get 3, so your limit is 3. Okay? If we were to quickly sketch that, what would it look like? So, okay, so 2x plus 1, this is a linear function, totally easy to use. At x equals 1, the y value is 3. And it's a closed circle there. And it's up 2 over 1, so that's how that looks. Okay? The other function is x cubed plus 2, and we know what x cubed plus 2 looks like. As x approaches 1, at x equals 1, this function is 3. It's an open circle, so we're just going to continue from that. And basically, right, that's going to look like that, right? So do you see how even graphically it supports that the limit is 3? Okay? You have to be very, very quick at being able to do this without a graph, just by the function. Yeah.
Should we draw like the x cubed plus 2 like more accurately, or could it just be like a sketch?
It could be a sketch.
Okay.
You should know like generally what it looks like and that they meet, especially at that partition.
So for homework, can we just draw like a rough sketch of the graph and then like?
Yeah, remember, yeah, so stick to this, what I said here. Okay? You could, yeah. Okay?
It doesn't have to be.
No, it doesn't have to be NASA precise. Okay? Okay, so take a look at this one. The graph is already given to you. So the limit as x approaches negative 2 from the left-hand side. So here is negative 2. From the left-hand side, what y value is it approaching? Here, 3. From the positive side, what y value is it approaching? -4. Here. Okay. So what's the limit as x approaches -2? dne. Okay. Right. Okay, so next one. The limit as x approaches 3 from the negative side. So where is x approaches 3? It's 1, 2, 3. This is the one. Okay, so as x, sometimes it helps to use your finger or your pencil to trace it, right? As x approaches 3, what y value is the graph approaching? Negative infinity. And from the other side, what y value is it approaching? Positive infinity. Now for positive infinity, you don't have to put the plus sign. Infinity is, it's like unwritten law. Okay, it's good enough. What's the dne? Because negative infinity and positive infinity are not the same. It is a very different situation if you have positive infinity dollars in your bank account or negative infinity dollars in your bank account. Chapter 11 time there. Okay, so let's go here. What about this one? Negative infinity, and here? Negative infinity. They're both going down to negative infinity as you approach 0. Remember, just trace with your finger. Now, here is the important part. This one, okay, it's negative infinity, negative infinity. Okay. You can say negative infinity slash dne. So if this is approaching negative infinity and this is approaching negative infinity, you can't say that all negative infinities have the same value because you don't know what negative infinity values are, right? So you have to be very, very careful. You can say, sometimes like the AP board will accept negative infinity on its own. Sometimes they will accept negative infinity on its own, or you can say dne, but if you said dne, you have to put negative infinity next to it because that dne is different from the dne above, right? Okay, so here the limit as x approaches 0. Okay, let's just think about this for a minute. This is 0.75, this is 0.75. That means these first bars here, right? This goes from negative 0.25 to positive 0.25, right? So as x approaches 0 from the minus side, right? What y value is the graph approaching? We don't know. Do you know? I don't know. I don't know if it's like here, 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 here. We don't know. So it's dne. Same thing from here, dne. So this whole thing is dne. Okay. So let's summarize all this, right? Where do points not exist? Right? Where do limits not exist? Well, there are certain situations. The first is when f of x approaches different values from the left and right of c. Okay? So for example, if you go up here, raise your hands for this, between like a, b, c, d, show me an example where the limit approaches different values. Yeah. B. Okay? Okay, another example is when f of x increases or decreases without bound, like they go to positive or negative infinity from the left or the right. No, not the one we just did. C or D. Infinity. When it this does not approach infinity, right? This one, the highest it approaches is what? You meant that one, yeah. And then the last one is when it oscillates very, very quickly, when it oscillates rapidly between two fixed values like number e. Okay? Yeah. Okay. So what about, okay, so until now we were finding limits as x approaches a number, -3, 2, 0, blah, blah, blah. How about limits at infinity? All right, so let's take a look at these limits at infinity. So this is the graph here. And okay, so for efficiency purposes, I've actually like given you the graphs here. On the homework, you might just be given the functions, and this is what I mean. Like for a graph like this, just put it in your calculator, sketch the graph for me. Now, okay, I'm saying it doesn't have to be NASA precise, but it still has to be done like professional looking, okay? Okay, and then you just kind of observe, right? So as x approaches positive infinity, this is going to what?
Positive infinity.
Is it? What y value is the graph approaching? -3. Really helps to trace along with your finger or with your pencil. How about as x approaches negative infinity? -3. Okay. As x approaches infinity with this sign, do you know? Where is it going to be? I don't know. Like, how do I even know where infinity is, right? And it's going to be somewhere between 1 and -1, but I don't even know where infinity is. So when we get to infinity, if that's even possible, is it here, 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 here? I don't know. So it's DNE. Okay, this is legit one of my favorite functions. Look at this one. Let's just explore the beauty of this for a minute. Okay, this is, okay, sine of 3 pi x is basically an oscillation, right? Okay, here I'll make it more exact, right? That's sine of 3 pi x. That's pretty much what it looks like. E to the x, how does e to the x look like? This. If you combine the two of them, e to the x, we say it dampens this curve, right? It kind of like exerts itself on top of that oscillation. So the entire oscillation takes the shape of e to the x. Isn't that the coolest thing you've ever seen in your life?
Yes.
Yes, there you go. All right, you just redeemed yourself, River, for all the other questions. All right, so do you see that? Okay? All right. So what happens as x approaches positive infinity? DNE, for sure. What about as x approaches negative infinity? 0 for sure. Isn't that fun and cool? Fun and cool, right? Yeah. So, you know, this is the first lesson. So hopefully it makes you feel a little bit better about, you know, managing this with the AP schedules as well.